Okay, good morning, everybody. We are presenting here or discussing here the topics of his PhD work. In this case, Lorenzo Vaquero is presenting his work on tracking of objects using a very hot topic, deep learning. He is going to present his work, and then we will discuss with him our main issues related to the work, or of course congratulate him for his work. I have read one of your papers related to this work yesterday, and it's a very good work, very interesting for discussing here. So thank you very much, Lorenzo, when you consider adequate.
Okay, thanks a lot, Dora. And thanks a lot, everyone, for coming here. Okay, my name is Lorenzo Vaquero, and I will present you the current state of my work titled Multiple Object Visual Tracking through Deep Convolutional Networks. The outline of this discussion will be as follows. First, I will introduce the motivation of our work, followed by two of our proposed approaches. Then I will close with the conclusions. I hope you all like it. Okay, as you may have guessed from the title, my work focuses on visual object tracking. So first of all, I'm going to tell you what is this all about. Visual object tracking consists in maintaining the identity of one or more objects detected through a video. This is, in the first frame of the sequence, we are given the objects of interest where the user wants to track. And our job is, for the subsequent frames, give the information of where are located those objects, maintaining their identity. For example, in this case, we are giving these cars to follow, and we show them in the subsequent frames of the video. This allows us not to only know their location and size in every moment, but also incorporate an additional dimension, time. In this way, we're able to detect behaviors, shape changes, and transformation. This tracking allows us to open a gateway to extract more information about what's happening in the scene. In this way, applications that build on top of trackers are able to perform routinary tasks, such as, for example, people counting, or more critical tasks, such as following vehicles from an UAV. Okay, so the thing is, if we want to perform this, there are many techniques that we can approach. Here I will show you an example of visual object tracking. As you can see, the output is shown via bounding boxes, and we're able to maintain the identity of all the risers in this video. As you can see, the system is able to track them despite the shape changes and transformations. So the question now is, how? How can we do this? Well, currently, visual object tracking is divided into two clearly differentiated trends: single object and multi-object tracking. Multi-object trackers run a detector on each frame. They then associate those detections, generating trajectories and assigning identifiers. On the other hand, single object trackers start from the location of the object. They define it as its appearance model, and then try to look for that object in each subsequent frame. Subsequently, each trend is divided into two branches. Multiple object trackers can be offline. This means that they need to process the whole video before making a single prediction, or online, which means that they can make predictions as they are processing frames. On the other hand, single object trackers are usually online. That's why we made the distinction regarding if they use discriminant and correlation filters or deep learning techniques. The latter are the most used nowadays because they offer the greatest accuracy and robustness. Okay, as you may imagine, each approach has its pros and cons. Multiple object trackers can handle several dozen objects. However, as they run a detector on each frame, they are heavily limited on the speed. And also, because of this detector, they are only allowed to track specific categories. They cannot track arbitrary objects because said detector must be pre-trained for each type of object. On the other hand, single object trackers, as they process videos online, most of them are very fast and are able to process video in real time. And also, as they are not dependent on detectors, they can track arbitrary objects. However, as their name implies, they can only track one target at a time. There are some systems that instantiate multiple single object trackers. However, this approach is unfeasible if we have many objects in the scene, as the speed will decrease exponentially. Since various computer vision applications operate in rich and varied environments, often having multiple objects of interest, they demand systems capable of tracking multiple objects in real time. And this is something that current solutions cannot provide. Therefore, we propose a multiple object tracker that employs single object tracking techniques efficiently. In this way, we have a solution that brings together the best of each approach, a system capable of tracking multiple objects in real time. Okay, as a starting point to develop architecture, we chose the tracker SiamFC, which is depicted here. Its architecture, simple but effective, is the forerunner of current visual object trackers. It allows the tracking of one object at very high speeds, offering excellent accuracy and robustness. The operation is as follows. As can be seen, for each new frame, the first thing it does is to crop and resize a search area, located in the last known position of the object. Then, with an AlexNet-based backbone, it extracts the features of said search area, to then compare it with the features from the previously extracted exemplar. This comparison is made through a cross-correlation operation, giving us a score map. After applying some shape and translation localization to the score map, we obtain the final size and location of the object. Keeping this architecture in mind, we developed our SiamMT network. As you can see, the inspiration is more than evident. However, as similar as the networks may seem, we have a number of fundamental changes. When our system receives a new frame, the first thing it does is to globally extract its features, using an AlexNet-based backbone that lacks padding. This is a unique characteristic of SiamMT, compared to single-object trackers, which only process a portion of the input image. By doing this, SiamMT is able to reuse the computations for the several objects that appear on the scene, very similar to how current object detectors work. Secondly, we can highlight our novel features crop and resize operation. In SiamMT, we crop features, not images. This operator is based on realign, but with only one sampling point per bin, and slightly modifying the coordinates transformation between images and features in order to allow it to work with backbones without padding. You see, when transforming image coordinates to feature coordinates, realign performs the red color path, simply dividing the coordinates by the stride of the backbone. As you can see, this yields incorrect results when the backbone phi lacks padding. Thus, in order to calculate the correct transformation, we have to follow the green color path, employing the effective size of the input image, whose calculation is here shown. Therefore, in order to obtain the correct coordinates, our first step consists in calculating the translation of the object when clipping the image to its effective size, to then transform those coordinates as realign will normally do. In this way, we obtain the correct coordinates when transforming image coordinates to feature coordinates in backbones without padding. Okay, finally, the last novelty incorporated in our architecture consists in the reformulation of the final similarity operation. To allow an efficient comparison of multiple feature maps, we have taken advantages of the properties of GPU architectures and developed a novel pairwise cross-correlation. This operation exploits the properties of the two-dimensional depthwise cross-correlation operator by appropriately stacking the exemplar and search area features tensors. Thanks to this, we obtain an operator mathematically equivalent to performing several cross-correlations sequentially, but at a fraction of its cost. Okay, in order to measure the performance of the system, we have conducted several benchmarks, both on VGA and HD video. We compared our proposal, SiamMT, against SiamFC and SiamFC MI, which is a version of SiamFC specially designed in order to be multiply instantiated. As can be seen, SiamMT is the slowest approach on both benchmarks when tracking a single object. However, as more objects are added, SiamMT's scalability begins to show, and from 5 objects on, it dominates both benchmarks, and it is able to follow at 25 FPS, which we consider real-time, 60 objects in VGA video and 40 objects in HD video. Meanwhile, SiamFC and SiamFC MI are only able to track 8 objects at real time. At 100 objects, SiamMT performs at 15 FPS, highlighting the capabilities of the developed architecture. But speed is not everything. A tracker must not only be fast, but also accurate. That's why we have also measured the tracking quality of SiamMT against the different state-of-the-art trackers often used in motion estimation. Additionally, we also evaluate SiamMT-W, a version of SiamMT that directly reuses the weights learned by SiamFC. This comparison is performed on different datasets, using the standard metrics defined by VOT real-time. Thus, for different speed thresholds, we obtain the accuracy and robustness of the systems. The accuracy is the average overlap between our predictions and the ground truth, and the robustness is the amount of frames that we're able to track an object without losing it. The chosen datasets represent several real scenarios with multiple objects and different categories. As can be seen, the accuracy and robustness obtained by SiamMT are superior to those of the existing approaches, with differences as large as 20 points. Specifically, those datasets where SiamMT really excels are those with a large number of objects, most notably MOD20 and BISDRONE. As for SiamMT-W, it obtains slightly worse results than SiamMT, but they are very competitive, considering that no retraining has been needed. These results suggest towards the extensibility of our architecture towards other SiamFC-based approaches, with a minimal effort on training. Following is an example of the system's operation. This video depicts an air show. The planes have been labeled on the first frame of the sequence, and we have extracted their exemplar features, here shown in the right-hand side. These features will not be modified during the tracking process. As you can see, for each new frame, we extract its features, here shown at the bottom. We then crop and resize those features, obtaining the exemplar features, and we compare them using our novel similarity operation in order to obtain these heat maps. These heat maps indicate the new coordinates for each object. In this other example, we can see how the system is able to differentiate between these runners from their facial features. We can see that it is very robust towards shape changes and also perspective changes. And in order to reaffirm that the system is able to handle several objects in real time, here we have several farming machinery. As you can see, the machines are in motion, they have a very heavy occlusion between them, and the camera is also in motion, which is in another difficulty. Okay, so due to the success of this paradigm of applying single object tracking techniques to multiple objects, we decided to continue our research in the same line. You see, SiamMT is very good, but it is based on a network that is already 5 years old, so there's still room for improvement. We can apply the latest advances in computer vision in order to make it perform better. Introducing SiamMOTION. The essence is the same as SiamMT, but as you can see, it has been highly revamped. Let's focus on the most significant changes. First of all, we maintain the global frame features extraction, as it is one of the enablers of the SiamMT architecture. Without this property, we wouldn't be able to apply all these kind of techniques to several dozen targets in real time. However, in SiamMOTION, we no longer use an AlexNet backbone without padding. We use a ResNet. This allows us to extract much deeper features and maintain the information at the edges of the image. This information at the edges is especially important, as most of the objects enter and leave the scene on the edge of the frame. Secondly, we introduce an inertial module. The previous network, as well as all single object trackers to date, search for the targets in their last known position. This is fine, but there is still room for improvement because there are some instances, for example, with very fast moving objects, where the object can leave the search area for one frame to another. To solve this, in SiamMOTION, we propose an inertial module that it is based on a multi-layer perceptron. It is fed by the output of the network, and it is able to make coarse predictions of the future location of the objects without resorting to visual information. This makes this module very fast. And it is key that this module is lightweight in order to not interfere with the real-time capabilities of the whole architecture. Regarding the acquisition of the search areas, in SiamMOTION, we still crop and resize features, not images. However, SiamMOTION's operation had a weakness, and it was that its crop and resize operator performed worse with very big or very small objects. To solve this, our new operation processes several layers of the ResNet at the same time. To do this, they merge its information using a feature pyramid network, and then perform the crop and resize using a modified realign operator on the most appropriate resolution. This allows us to track objects of very different sizes without resorting to weird gimmicks. Okay, SiamMOTION's similarity operation compares features, regardless of where they came from. This blind comparison could be a problem, as too much weight may be given to information proceeding from the background of the scene or other unrelated objects. To minimize this effect, we introduce the attention mechanism here shown, in order to prove the features and enrich the information belonging to the object of interest. This attention mechanism is based on transformers and applies two types of attention to the exemplars and the search areas in a Siamese manner. With the self-attention, we learn strong context information and emphasize channel-wise features. And with the cross-attention, we aggregate interdependencies between the exemplar and the search area. All this allows us to suppress the effect of distractors. Another substantial change of this update is the update of the similarity operation. We now use a region proposal network, specifically designed for multiple object tracking. An RPN subnetwork, like the one shown here, is based on the use of anchors. These are rectangles of different shapes and scalar ratios that slide across the search area. Thus, the objective of the network is to predict the probability that each anchor contains an object or not, and to fit it to its bounding box accordingly. In order to achieve this, we employ two branches. One branch to classify each anchor as an object or background, and another branch to regress said anchors in order to fit the bounding box accordingly. This removes the need for performing several searches across different scales, like SiamMOTION did. However, our RPN has a key difference compared to other region proposal networks, and it is that the core of our similarity operation is powered by the pairwise depthwise cross-correlation we introduced in SiamMOTION. This allows it to perform multiple pairwise comparisons in an efficient and scalable manner. In return, it introduces a little bit of complexity, as we must reshape the input and output tensors, but this is more than justified. Okay, once we have our classification and regressions, we could transfer them to the original frame. However, in SiamMOTION, we add another component in order to refine same predictions. We introduce a multi-object penalization model, which takes into account the predictions for all objects together in order to modify the probabilities for each anchor. It is composed of 4 types of penalization: a spatial penalization, a shape penalization, a morphological penalization, and an interaction penalization. After applying these penalizations together, we now have the final predictions of our network. This whole process is repeated for each new frame, allowing us to track several dozens of objects online and in real time. As can be seen in this figure, the accuracy and robustness obtained by SiamMOTION are superior to those of the existing approaches, surpassing them in every benchmark. This demonstrates the effectiveness of the new components introduced and hints towards the fact that this architecture can be further enhanced. All this translates in better performance both quantitatively and quantitatively. For example, in this example shown, SiamMT is not able, SiamMT is not able to detect the shape change of the cars, while SiamMOTION does, the aspect ratio change. Finally, we will present the conclusions that we have drawn so far from this work and its future, from this project and its future work. With the development of SiamMT, we have created a new line of multi-object tracking without the need of continuous redetections. This makes SiamMT the first deep learning-based arbitrary multi-object tracker. To achieve this, it applies single-object tracking techniques to multiple targets in an efficient and scalable manner, on behalf of its global extraction of frame features, the reformulation of the realign operator, and the optimized similarity operation. It offers good tracking quality for several dozens of objects. And moreover, since it is based on SiamFC, it is able to directly reuse the weights learned by it, obtaining very good results and suggesting towards the extensibility of SiamMT to other SiamFC-based architectures. With the development of SiamMOTION, we have been able to further confirm the viability of this paradigm. It incorporates new ideas that improve the quality of the tracking, each one focused on solving one different problem of the previous network. Regarding the future work, a clear option is to continue exploiting the architecture, incorporating new modules in order to improve the tracking quality. Specifically, it would be very nice to incorporate and pay a closer attention to the distractors management and or modify the head of the network in order to perform a more transformer-like pure similarity operation. Also, as we have many objects in the scene, the use of bounding boxes is sometimes not very illustrative. This is why it will be very nice to modify the output of our network in order to also include segmentation information. This is producing a per pixel output. Even though this may not be the final output of the network, the tracking quality may be improved by producing better bounding boxes, as it occurs with the masked RCNN detector. And of course, the interesting part of this type of technologies is to incorporate them in real applications. This is why the idea of integrating SiamMOTION in a real use case, such as an assisted video annotator, is very tempting. And lastly, another possibility is to integrate this algorithm into low-power devices in order to be able to perform track at the edge. This approach has already been explored with SiamMT on an NVIDIA Jetson, as the AlexNet backbone is more lightweight than ResNet. But this is something that still requires further development. And that's all. Thanks a lot for all of you and for your attention. If you don't have any questions or comments, please feel free to ask them. Thank you.
Thank you very much for the presentation. It was very clear what the work is too deep for presenting in only 10 or 15 minutes. Well, I forgot before to say that the supervisors of the work of Lorenzo are Manuel Mucientes and Victor Brea, the PhD supervisors. If you have any comments or questions, please feel free to ask or comment to Lorenzo. While you are thinking, I'm going to make a question and some comments on the work. The presentation was very interesting because you use figures explaining the architecture of the networks. But we need a first explanation explaining what is the characteristic of a CMS network.
Mhm.
You talk about SIAM networks and SIAM FC, SIAM.
Yes.
What is a SIAMS network?
The thing is, for visual object tracking, in the beginning, the most widely used technique were the use of correlation filters. However, suddenly in this field, novel approach appeared that was SiamFC with the proposal of these Siamese networks. The idea is to employ a backbone, a fully convolutional backbone, in order to extract characteristics of the images. And this backbone is learned by the network itself. And the Siamese part is that we apply the same backbone on both the search area and the exemplary image. This allows us for much better convergence of the algorithm and for it to learn fast. So the idea is that on these three AlexNet-based backbones, the weights are shared, they are learned together through the process of backpropagation, and for inference, the same function is applied to the exemplar and the search area image. So the last thing that remains to do is to merge those Siamese branches using a similarity operation. In the case of SiamFC, a convolutional layer. I don't know if I made myself clear or not.
Yeah.
Okay.
Very clear. It's very interesting. Seeing the architecture represented here and the in SiamMOTION,
Mm-hmm.
The computational cost is evident. You talk about one optimization based on drawing correlations. You develop drawing correlations in order to accelerate the process and trying to avoid time exploiting the GPU architecture.
Yes.
And my main question here is related to the computational cost. As you talk about real time,
Mm-hmm.
I don't remember how did you define real time in this context?
In this, well, as you already know, real time depends on the application. For some applications, it might be 16 FPS or even as low as 5 FPS. Here, in our case, as most of the approaches do, we define real time on the threshold of 25 FPS with an, I would say, consumer use grade hardware. In this example, we define real time as 25 FPS using an NVIDIA Titan XP GPU.
So this real time limits the number of objects that you can track.
Yes, both the real time heavily influences the resolution of the input frame because more pixels require more time to process them, and both the objects we can track because there are some operations that are not totally independent of the number of objects, and they increase its time with the number of objects. For example, I don't know if I have it here. Yes, this is the measurement of times per operation for SiamFC and SiamMT. As you can see, for each object, SiamFC times increases linearly, I would say, so more objects, more time. And in SiamMT, we have an almost flat figure. However, as you can see, for example, the blue line with the bounding box update and the similarity operation slightly increases with the number of objects. So we're still bounded by set number.
So the number of objects could be increased much more than in this case.
It could be increased. We have made some experiments that our newest systems is able to top out at 100 objects in real time. But yeah, even though the added cost for adding new objects is slight, with many more objects, we start losing the capabilities of running in real time.
This time includes the learning process?
No. This is only the time of inference, because this neural network is first trained on very big databases of video and also images. And once we do this, the weights are frozen and we're just performing inference with no further retraining needed. That's why we're also able to track arbitrary objects.
Well, for example, if we are in one of your examples in a street, for example, in a road, you can train your network and follow different cars of the cars that you use for learning.
The thing is, as we employ I will use this slide as an example. As we have the initial appearance of the object and we extract its exemplar features, we need no further train because for each frame we compare each search area with said exemplar. So there is no retraining needed for each object. We have the reference, the aspect of the object, its aspect model here in the exemplars.
How many examples are necessary, for example, for tracking a row?
Normally, we only use one frame per object. I mean, the first frame it appears, we get its appearance for them. We have been exploring some alternatives in order to increase like the memory of our system has of the object in order to update said exemplar information, but so far we haven't been able to obtain good results with this update because on the first frame we have the ground truth of the objects and we are 100% sure that the object is in there. However, if we attempt to update the exemplar with our predictions, sometimes said predictions can be noisy and just harm the network.
Very interesting. And what can you say about the inference, the training time?
I can see that it takes very long.
For example?
Yes, it is a pain in order to try different approaches because sometimes we have to wait like 4 days in order to finish those those trainings. It depends also on the network. The SiamMOTION one takes between 4 and 5 days to train. The SiamMT one took like 2 days. But yeah, the thing I can say that the train.
How many frames?
For
example, in one of these data sets that you use for comparison.
Mostly you mean the thing is for training? For training, we mostly use 4 data sets, which are ILS VRC video, ILS VRC image, YouTube bounding boxes, and Coco images. And all of those, I think it is close to 1 million frames, I would say, or something like that. So, and also because of this Siamese architecture of exemplar and the search area, the training process is not a conventional training process where each epoch we analyze fully the data set once, because we perform permutations, and in one epoch we do not scan all the frames in the data set necessarily. I don't know if that makes sense. Okay.
Makes sense. So these applications need to be applied to cases where you have a high enough number of frames for learning.
Yes, that's a big problem of these kind of trackers that need a lot of information in order to be able to train. However, as it is a tracker able to handle arbitrary objects, arbitrary meaning no matter the category, it can follow a cat, a dog, or a hand, we don't need for applications specific training. For example, if we want to apply to air traffic control, we can just take the pre-trained tracker out of the box and it will perform okay. Other trackers that employ detectors for each frame must be pre-trained for each scenario, and that's where the big problem of not having enough data appears. Thank you.
Congratulations, Lorenzo. I have a question. What happens if a real world, when you're capturing with camera, and imagine that some object pass in front of the camera? What happens? Able to continue tracking the object, or
The thing is, well, thanks a lot for your question. The thing is, these networks are robust to these kind of occlusions. However, as this is what we would consider a low-level tracker, with meaning that more specific applications will be built on top of it, it is robust to, I would say, short-term occlusions. The thing is, if for example you are recording a video and you put your hand in front of it, you pass your hand, the network will be able to, on those frames where the hand appears, just do not move the object, predict that the object has not moved, and when you remove your hand, it will be able to say, oh, okay, the object was still here. However, if you are talking about long-term occlusions, for example, an object that a car that enters the tunnel, the network will not be able to predict that. If we have a scene where a car enters the tunnel, the network will be stuck on the entrance of the tunnel trying to find the object again. It will not be as smart as to know that the object will appear on the exit of the tunnel. With our inertial module, we can somewhat mitigate those things, but the inertial module predicts also short term. So if it is a short tunnel, it will work, but if the object is occluded for, let's say, 10 frames and then it appears in a different place of the video, then our tracker won't work, and we will need some redetection technique.
This is because you are looking in the previous frame, more or less where the object was, no?
Yes, this is due to the fact that we employ search areas. We could search for the object on the entire frame, but on 90% of the cases, this will be a waste of resources because most of the time the object does not move from the search area. And in those cases of fast-moving objects, that's when we incorporated our inertial module. But yeah, the tracker is far from perfect in the sense that it cannot track everything. Thank you.
About the question on the how you manage objects in motion.
Mm-hmm.
Reason to use a deep learning based method. I don't know if you can use some traditional method of setting the object in one size and then infer the velocity of the object. I mean, there is
yes,
enough easy to use, or is it more accurate, more performance?
You mean using a multi-layer perceptron instead of just a physics equation or a Kalman filter or something like that?
Yes.
Well, the thing is that the multi-layer perceptron is a very lightweight component because it's just a bunch of multiplications and sums. And also the thing is that as we don't have perfect predictions of the object, we have the output from our neural network and it has some noise. We have seen that this inertial module is somewhat able to learn the noise produced by the network and adapt to it. And it produces much smoother prediction than if we just took the previous location and the next location. I don't know if I answered. Okay.
Question, additional question or comment? We have a last question.
Okay.
How would you improve the computational cost of the learning process in your architecture? Do you have any model especially costly that could be improved, or the execution time reduced, improving the GPU execution or the projection of the algorithm over the architecture? Or?
I think that one of the first approaches I would take would consist in first have the feature structure computed, learned in the traditional way, and then in order to train the attention module, the similarity module, and so on, have the exemplars and search area features previously extracted from the features extractor that will be frozen, and then just do the training on exemplar and search area tensors that are very small compared to full HD images. In this way, I think we will have a still heavy training time in order to train the feature extractor. However, in order to test new similarity modules, if they can be separated from the learning of the backbone, then we will be able to test things very fast. However, we will run into storage issues because we will have to store the exemplars and search areas tensor for that million of frames and a lot of objects. So that will be another challenge. But yeah, I think that at least that would be my first approach to try to improve the learning speed of the network.
Interesting, because only a small change could reduce considerably the learning time and one way of promoting the use of the architecture, because at this moment GPUs are being used very efficiently, and GPU-based architecture are being used very efficiently for deep learning algorithms in general, using TensorFlow and all these tools. But an effort thinking on dividing the work, the other part of the work that is not the network itself, it can improve considerably the execution time and make more appealing the solution that one and more usable. I encourage you to think about the issue for future work if you have the opportunity. I congratulate you for your work and your resources. It's very interesting, and you have demonstrated that you know the work very deeply, so that you thought very deeply on the problem. So congratulations. Thanks everybody for coming to the doctoral meeting session.